Hello everyone. I just find this very useful software that I can use to capture my screen and my voice simultaneously. So I think I'm gonna just try to use this particular software to record myself instead of going to the One Button Studio. Okay, so as I promised, this class or this additional lecture would be on the review of the 3D elasticity. And let's just get started real quickly and then we can finish on time. So consider that you have a three-dimensional space, okay, and inside of that you have this continuum body, which in this case I draw it as a potato here. And this continuous body occupied this particular region in the Euclidean space, where this body belongs to the three-dimensional real space, as is R3. And this B is what we call the reference configuration. And each point belongs to this particular body B is X, and it's just a particle inside of this continuum body. And for each of the points, basically you could have some displacement, right, to move this body to another position, and this U is the displacement or the displacement field. Okay, and then because it's in 3D, it's not like the previous case that we have as just in 1D. Each particular point X is a vector which contains three different components, x1, x2, and x3, in this Cartesian or this coordinate system. Okay, and then the linear string tensor can also be represented inside of this body, where this epsilon is defined as the linear string tensor relative to the Cartesian system x1, x2, x3. Basically, it's just this particle x, and it has components c or epsilon ij, and where this epsilon ij follow the same rule as a symmetric tensor. Okay, so if you go back to our lecture 5, it is mainly about the tensor and vector operation. So instead of that, you will find the different operators or different operations for a symmetric tensor. And by definition, epsilon ij is defined as, because it's symmetric, so it's 1/2 partial ui over xj plus uj over xi. Okay, and it can also be written as u comma j plus uj comma I, where I and j all takes 1 to 3 because it's in 3D, and u is the displacement field that we have already defined. Okay, and then since it's symmetric, we know that epsilon ij equals to epsilon ji. Epsilon, so if we write it in a symbolic form, that means epsilon equals to epsilon transpose, and this epsilon is symmetric. Okay, and then the third important thing inside of the elasticity, the traction vector and the stress tensor. Okay, we would first define what is the traction vector. So a traction vector is defined as some traction applied to a small surface or to some certain surface for this particular body. So you have a body in 3D, that means the boundary would be a surface, right? Because if the body is in 3D, then the surface, the boundary would be in 2D, that is a surface. And then in the Cartesian coordinates, for this small surface where this traction is applied or acting on, it can be represented as the component or the composition of the three different coordinates sitting acting together. So that means if you have a traction T acting on this particular surface, then it can always be decomposed into three different components based on the Cartesian coordinates, which in this case would be E1, E2, and then E3, right? Okay, and then once you put this particular traction into all the three components, then basically it's gonna just be something like this, where you're gonna have T1, and then where's the T2? T2 is here, T2, and then T3, right? Without any doubt, it can be decomposed into three different components. And then you could write your traction vector to T1 times the unit normal or unit vector on that particular direction plus T2 times E2 plus T3 times E3. Okay, and this is my traction vector. And notice this traction vector is acting on the surface. So it really matters which surface is this traction vector acting on. And in this case, usually we define it as if we define it related, or this traction vector is related to the normal vector of that particular surface. And in this case, as what we drawed, we actually specify this traction vector to be a traction vector acting on the surface, where E3 is the normal vector. So since E3 direction is the normal direction, T E3 equals to T. Okay, so we specify this traction vector to this E3 traction vector. Okay, and then we wanted to relate this traction vector to the component of the stress tensor. Okay, so if we represent each Tj by sigma ij, where inside of this sigma ij, the two different notation or two different indices here, I means the direction of the normal direction, the direction of the normal direction, or the normal vector. Vector J is the direction of the component. Then is T on the surface where E3 is the normal vector, can be represented as sigma 3,1 E1 plus sigma 3,2 E2 plus sigma 3,3 E3. Okay, so basically this I represents which surface is that, and this J represents the three different components inside of this vector. Okay. Okay, then if you repeat the process for the other two planes with the normal direction E2 and E1, finally you could have three different traction vector acting on three different directions or three different surfaces. And if you write them together, then it can be represented as follows, the three of them together. Okay, then if we further combine all the three traction vectors into one small cubic, as I just plotted here, basically, let's see, we could start from the one with what we did before, the E3 as the normal vector. So that would be either the top or the bottom surface, right? So let's just consider that it is the top surface. So on this particular surface, we could have this traction vector sitting there where the three components are sigma 3 3 for the normal component or the normal direction of this particular surface, and then sigma 3 2 for E2, and then sigma 3 1 for E1. Similarly, you could write it for all the surface here. Okay, so I'm gonna just write it on the surface with E2 as the normal vector. So then this is sigma 2 2, sigma 2 3, sigma 2 sigma 2 1, right? And then you would have another one with E1 as a normal vector, where this is gonna be a sigma 1 1, okay? And this is gonna be a sigma 1 3 and sigma 1 2, okay? So once you combine all the three traction vectors onto this small cubic, then we just assume that this small cubic is shrinking and shrinking and shrinking, getting smaller and smaller until it goes into just a single point at the origin, here, 0, 0, and 0. Okay, if that will be the case, then all the three traction vectors, or all, in this case, 9 components, are acting at the origin. Okay, so they are your stresses acting at the origin. Okay, and if that is the case, we could further write out the 9 stress components at that particular point, 0, 0, 0, right? So when you having all of them sitting together, then you will notice that basically you have 9 unknowns here, right? 3 by 3. And then because it's the stress, it should have some relation with the traction, as we have just seen before, because this E1, E2, E3 are the normal vector on the 3 different directions and for this Cartesian coordinates. So from Cauchy's law, we know that Ti actually equals to sigma ij nj, and for the symbolic form, basically T equals to, choose this color, T equals to sigma n, right? Where this n, the n vector niei is the normal vector to the surface. T equals to tiei is the traction vector acting on that, where that means this particular surface, where this n is the normal vector, on that surface. Okay. So now we have a relation between the traction vector and the stress tensor. Okay. And then the next step, since we have that, we know that this traction vector can be acting on either direction on that particular surface, right? It is not necessary to be the normal or the tangential component, but we can, of course, decompose that into 2 different components, which would be important for us to know the traction on that particular surface. We could definitely decompose it into normal and shear stress, where the normal means it's just orthogonal to the tangential, or it's just in this parallel to the normal direction. The shear stress means it's orthogonal to the normal stress. Okay, so the normal stress, we can write it as n dot product with t in the direction of n, right? And basically it's just TINI. So we know that if you have a notation that says that it's TINNI or something where this I is repeated, it means that it is a summary notation, and everything needs to be summed together. So basically it's T1 and 1 plus T2 and 2 plus T3 and 3. Okay, we all know that. And then the shear stress, which is the tangential component, just simply equals to the square root of your Tn, the normal of that, minus your normal stress. Okay, because the normal stress is the summation, needs to obey the summation notation, so it's actually a scalar, and then the shear stress is also a scalar. Okay, for this small example here, if you have a random stress as sigma ij, which is a 3×3 stress taking this form, and then if you wanted to determine the traction vector acting on the plane with norm equals to this particular one, and then you could also, once you define the traction vector, you could then define the normal stress and then the shear stress, right? So if you want to do that, first for part A, the traction from the definition we know equals to the tensor sigma tensor product, so the tensor acting on a vector, which is a normal vector, right? So then with the matrix multiplication, we know we just need to substitute everything, okay? And then once we have the traction vector, then we just use the normal vector dot with your tensor, or your traction vector, right? And with the dot product, it means basically you need to first transfer or transpose the normal vector, because we know that the normal stress is a scalar, right? And this is actually a dot product. Okay, so after this dot product, finally you would get a scalar, right? So then makes it a first we transpose the normal vector and multiply by the traction vector. Okay, and then for the shear stress or the tangential component, we could simply just do the square root of Tn square minus sigma n square. And then finally we got the answer for that. So from this small example, we just wanted to clarify that we know what is the tensor acting on a vector, how to do that, which basically just the matrix multiplication, and then how to do the dot product, and then how to take the other component by doing the square root. Okay, so it's really easy. Now we go to the next part. Okay, we've already defined the traction vector, and then based on that traction vector, we define what is the coherent stress, sigma. Okay, and for this sigma, we also know that it needs to be a symmetric tensor, right? Basically, sigma ij equals to sigma ji. Okay, if we denote by this S to be the set of all symmetric tensors, okay, then the dimension of this particular set equals to 6 in a three-dimensional space. Okay, why is that? Because your sigma ij is symmetric. So basically, all the unknowns that you have would be first all the three, orthogonal terms, and then because of the symmetry, sigma 1 2 equals to sigma 2 1, 1 3 equals to 3 1, 2 3 equals to 3 2. So accounting total, you are gonna have 6 unknowns. In total, right? That's why the dimension for this particular symmetric tensor is only 6. Okay, and based on the definition for isotropic state of the stress, sigma ij, if it is isotropic stress, then basically it means it needs to be equal to sigma 0, which is a constant, times delta ij. Or if you write it in the matrix form, Then for all the diagonal terms, it to be constant, the same, equals to sigma 0, and then all the other terms are 0. Okay, so two different requirements. First, same stress value in every direction, make it isotropic, and then there's no shear stress. The example for this particular state is the hydrostatic state of stress. So usually it is used to represent in fluid mechanics. It will represent in fluid at rest. Okay, then it is in the hydrostatic state, and that is why it is called the hydrostatic state. And the definition for that is the same as isotropic state, except for that we give it a specific name or a specific parameter or a constant value here, okay, which is this P, and this P is the fluid hydrostatic pressure. Okay, so two different forms, the index form and then the symbolic form. Both are valid, and then this P has its own meaning. Okay, so this is more or less like a specific or a just a special case for the stress, which is the isotropic state. Okay, but usually the traction can be, you can have all the values sitting there as activated. Okay, so that is part C of the linear elasticity, or 3D, not actually linear, but 3D elasticity. The traction, the stress tensor, and then the traction vector. Okay, and then we go into part D, which is the boundary condition for 3D elasticity problem. So the boundary condition for that is also basically the same as in 1D. You would have some traction boundary and some displacement boundary, where the traction boundary is you have some traction acting on that, some surface traction, and then the displacement, you just have fixed or roller, or you have some displacement applied there. And one thing to note is that the boundary that you have is a union of your traction and your displacement boundary, and then the intersection of these two particular boundaries is empty. Okay, so these are the two requirements if you're setting the boundary conditions. And once we have all this defined, we can go into the boundary value problem that we want to solve. So first, we assume there's no dynamic, but you can simply add the dynamic into it. If we assume there's no dynamic, then the governing system of equations in a linear elasticity or nonlinear small deformation elasticity would just be the diff of sigma plus rho b equals to 0. Notice that because it's in 3D, so everything needs to be in either vector or tensor form, right? Okay, then the stress tensor, we know that is symmetric. And in the index form, that's basically just sigma ij over j plus rho b I equals to 0, and then sigma ij equals to sigma ji. Again, I wanted to emphasize that for sigma ij comma j, there's a repeated indices, this j, so basically we need to sum it over. Okay, and then rho is the density, we know, and b is the body force, right? This 3D boundary value problem is also applicable to a 1D problem, right? So it does not mean that it extended to 3D and it's, not compatible for 1D. It's going to always be backward compatible. So if you put that into a 1D, then let's see, in this 1D problem, the sigma ij would just have a sigma in the x direction, sigma 1, 1, and all the other components to be 0, right? And the boundary or the body that you're interested in would just be this particular bar from 0 to L. And the boundary for that is just the 2 points, 0 and L, right? So this means that it's only 0 and L, okay? And then this B is the all the things inside of this bar. Okay, and then since it's 1D, so it's gonna just be d sigma over dx plus rho b equals to 0. Okay, and the boundaries are, first, left hand side is either, so on your, so left hand side is fixed, and then you could have some displacement on some other side. So for your Dirichlet boundary condition, it's just gonna be ui equals to ui bar, where this ui bar can either be 0 or some number. And on your traction boundary of sigma ij and I equals to applied traction, which can be Ti. Okay, you could also have some internal force, like as this internal body force, like this B here, right? Okay. So if we have this not initial, but this boundary value problem in hand, because it's static, okay, now the given data for us is that we have, this body that we know, and then we have some applied displacement and some applied traction and some applied body force, right? And what we wanted to calculate is first displacement, of course, right, on the unknown nodes, and then the traction. So in 3D, the displacement that we have would always just be, for a particular node, it's always going to be 3 different displacement, x, y, and then z, right? And then a stress vector, as we just figured out before, that's the dimension of that is 6 because it's symmetric. So which makes it in total 9 unknowns that we want to solve, right? And then the equation we have now is the governing system of equations, right? So basically just the equilibrium equations that we have. And in total, we have 3, because basically we have sigma ij comma j plus rho bi equals to 0, and I takes 1 to 3, right? So in total, we have 3. And then the conclusion that we have is that the difference between the unknowns and the equations that we have is actually 6. So we are missing 6 equations to solve all the unknowns that we have, because for each unknown we need 1 equation to solve that, right? Okay, so how are we gonna try to fill in the hole or to make it up? That will be through the constitutive equations. Okay, so then these constitutive equations are the parts that, for small deformation, it is the part that if you can have some nonlinearity through the material nonlinearity going into these constitutive equations, okay? And for the plasticity, then the constitutive equations would also be different compared with elastic part. And for a classical example in the linear elasticity, we would take the just the linear elasticity as an example, where the stress-strain relation is as follows: sigma ij equals to Cij KL times epsilon KL, where Cij KL is the tensor of the material moduli. Okay, and it's a fourth order tensor actually. Okay, and some remarks on this material moduli. First, Cijkl equals to Cijikl equals toCijlk. So basically, I'm switching the order of the small indices here, where in this case, it just means that it has the minor symmetry, okay? And why is that? Basically, it's just because that your strain and your stress, both of them are symmetric, okay? And second, Cijkl equals to Cklij, which means that the major symmetry is also satisfied here. Why is that? Because for this linear elasticity, we first assume that it's hyperelastic material. Okay, so it is true for hyperelastic materials. And then based on these two remarks, we could further do some investigation for this particular material moduli. First, if without anything, we have this first order, tensor CIJKL, then because of we have IJKL, 4 different indices here, so in total, it would have 81 independent constant, right? So it's just 3 by 3 by 3 by 3, okay? And by hyperelastic, we could further reduce it to 21 independent constant, which is good, right? And then further, if we assume isotropic, which means the strange functional that you use to derive this material moduli, the W is rotationally invariant. Excuse me. Okay. So this W has nothing to do with the direction that you have. That's why it is isotropic. Okay. Then if under this assumption, you would only have 2 independent constant, which are the Lamis constant, lambda, and mu. Okay? So with these 2 in hand, you can write your CIJKL as the follows. So it's lambda times the identity cross product identity plus 2 mu times the second order of this identity. Okay. You could also, start from the sigma ij representation, and then use the idea that CIJKL equals to partial of sigma ij over epsilon KL, and then derive the CIJKL expression. That also works. Okay. So for the classical constitutive equation of linear elasticity, there's another condition on the CIJKL aside from the isotropy, which is the strong ellipticity. Or the strong ellipticity. So what does that mean? Basically, it just means that this CIJKL that you have need to follow some physical phenomenon or the physical observations that you noticed in the real life. So if you consider an elastic rod, okay, strong ellipticity tells us that if you increase this particular elastic rod in length, if you pulled, then you will increase the length of this elastic rod. Okay, so that is related with basically the Young's modulus or the elastic modulus that you have. Because the elastic modulus is bigger than 0, so when you pull this particular elastic rod, the length would increase. Okay, and then the second, if you're under some pressure, then the volume would decrease. That is because your kappa is bigger than 0, where this is the bulk modulus. Okay, and then third, if you have a positive shear stress acting on that, you would have a positive shear strain. Okay, that is basically because your mu is bigger than 0, where this is the shear modulus. And lastly, okay, the pure tensile stress should produce a contraction in the normal direction. Okay, so that's basically because of the Possel's effect. So that means your mu need to be between 0 to 1/2 Poisson's ratio. Okay, When your Poisson's ratio equals to 1/2, it means it's incompressible. And if it's between 0 to 1/2, then it means it's compressible. So you should have some contraction in the other direction. We also noticed that in our previous coding for the nonlinear finite element class 3. And so this is gonna be all for this very short 3D elasticity review. And I hope that this would work if I'm recording myself okay and correctly. And then if it is fine, then I'm gonna just upload it to the YouTube, and then you could try to view it there. Okay, I'm gonna also upload the notes and then the handout there, so that you can follow this particular video and then together with the handout to fill in any missing part in there, as well as the 4 notes would also be there. Okay, sounds good.